Welcome to section 8.1, arc length. In this video, which we titled The Length of a Curve, our objective is to introduce arc length as a quantity defined through integration. So before we even get to that point, let's talk about length in general. So let's gain some intuition. When we talk about 2 points, P and Q, we talk about the distance between those 2 points as the length of the curve, the straight line curve between them. So straight line curve, a line segment, right? And so the way that we typically define this, the distance between P and Q, which we might also write in other notations, but we'll just call it this for now, is the square root of the difference between the two x values plus the difference of the two y values squared. And that is where P is x1, y1, and Q is x2, x2, y2. Okay. So knowing this, we can find the length of any line segment, right? And so our first example is, if we want to define the length of a curve, okay, what is the length of a straight line curve? And it shouldn't be too hard to see that what we're going to do here is this is the exact same formulation that we want to use. So for context, let's say we're looking at a function where we have a beginning point and an end point. So I have A and B. I've got f of A and f of B, and these are two y values for this function, but it's a straight line function. So what does this function look like? So f of x equals, and I'm going to assume that f of A is so zero can be A. In that case, it's going to be f of b minus f of a over b minus a, x plus f of a, because I'm going to assume that a is 0, okay? Now, this is a constant, this is a linear function, right? So mx plus b is another way of thinking about this, but we are past that sort of notation. And so the length of this curve from A to B, right, which we will denote L, is, as we found, right, it's going to be, again, the square root of the differences in the x values, so b minus a squared plus f of b minus f of a squared. Okay. So that's applying the Euclidean distance formula that we just found, right? And this gives us the exact length of that curve. So, but let me write this a little bit differently, okay? Because two things, right? So when we write this out, notice that what we're really saying is this is the difference in the x values squared plus the difference in the y values squared, square rooted. And we're going to apply something here to make this more manageable in the next generalization of length of the curve. So our question now fundamentally is, what is the length for any curve along x equals a to x equals b. So for instance, if we instead had something that looked like this. We had a f of a here, b f of b. We couldn't apply the same formula here because that would give us the straight line from a to b, and that's not the length of the curve. However, this is where we're going to apply that notion of infinitesimal. If we break up our interval into smaller pieces, then maybe we can approximate just one piece of the segment. So let's focus on one piece of the segment. I'm going to call this the ith segment. And we'll need another page to formalize this, okay? So the length over x sub I minus 1 to x sub I, where if we drop down two vertical lines from the curve down to the x-axis, we find the xi and the x sub I minus 1 is approximately L sub I equals, and now we can apply this idea here. So that's going to be x sub I minus x sub I minus 1 squared plus f of x sub I minus f of x sub I minus 1 squared, square rooted. Okay, so again, here is delta x, here's delta y, okay? And this is what we're doing here is we're really saying that line segment, the piece here, we're going to approximate it using a line segment, and because we've taken a small, tiny piece of this curve, it's close enough. It's actually pretty close, right? So in other words, what we've done is we've taken this curve and replaced it piecemeal by little tiny segments like this that are all straight line segments. You may guess where we're going here, okay? So it's time to build the arc length function. Well, I should say the arc length of a curve, okay? So again, what's our context? We're gonna start with, we've broken up, oops. A to B, that interval, into n subintervals of equal width delta x. Okay. Then we're saying L is the adding up all these tiny little well, they're not infinitesimal yet, but all these approximating little lengths. So from I equals 1 to n of the L sub i's, which is the sum from I equals 1 to n of the square root of what I'm going to call now delta x squared plus f of x sub I minus f of x sub I minus 1 squared, absolute value. I mean, not absolute value, square rooted. But how do we work with this? So how are we going to be able to find what this actually is equal to? And here's where we're going to use a wonderful result that, as I promised in Calc 1, comes up again and again to make things easier for us. This expression here, by the mean value theorem, there is such a number, x sub I star, such that this difference is equal to the derivative at f x sub I star times x sub I minus x sub I minus 1. So for some x sub I star in the ith subinterval. This is the mean value theorem, correct? This means we had to have assumed some things about f, right? So the functions that we're working with here are what we call smooth, okay? So they are differentiable. They're differentiable over this entire interval. If they're not, then we couldn't do this. But nuances that we're going to ignore as we move forward because all the functions that we work with are nice. Right. And so that means that we can write this expression now, this sum, as square root of delta x squared plus f prime of x sub I star squared times delta x squared. Because ultimately, x sub I minus x sub I minus 1 is just delta x. And very nicely, this means that we can pull out that delta x from the square root. So it's going to look like the square root of 1 plus f prime of x sub I star squared times delta x, because we pulled it out of the denominator. I mean, out of the radical. But this is all approximate, right? To actually really truly find the length, we have to take the limit as n goes to infinity. So smaller subintervals means more accurate tiny line segments that we're replacing the curve with. And so as we take n to infinity, this should start to look familiar. So remember that each x sub I star is a sample point somewhere, or is the equivalent of a sample point somewhere in that subinterval, the ith subinterval. And in the limit, it doesn't matter which number that is, right? This comes from the mean value theorem, but it really is just any x value in that interval. So what really we're doing here is we're Riemann summing. This is actually an integral. So we say this is the integral from a to b, because that's the left endpoint, the right endpoint, of the square root 1 plus f prime of x squared dx. Okay, so let's identify the pieces here, right? So this right here is telling us we're adding up all these infinitesimal little segments. This is the integrand. And here's your delta x. In the limit, they are equal to each other. So our infinitesimal piece is the dx times the square root expression, okay? Well, so there it is. That's the arc length formula. So given we know what f is, and given f is differentiable, then from any point x, from a to b, right, we can find the length using this integral. And so just to illustrate what we're doing here, I'm going to just kind of set up the integral for one of these. So we're going to find the length of the curve. I'm going to just set up the integral here. I'm not going to actually compute it, okay? Find the length of the curve of y equals ln cosine of x from x equals 0 to x equals pi over 3. Okay, so this really is saying that our function that we're looking at here is ln of cosine of x. So our derivative, which, you know, we have to look at the correct domain and make sure that it is differentiable, but these functions that we're working with are differentiable. Okay, so just go ahead. So the derivative of ln is u prime over u. So the derivative of cosine over cosine, which is negative sine of x over cosine of x, which is negative tangent of x. Cool. Then, if this is the derivative function, right, then the length of this curve from 0 to pi over 3 is given as the integral from 0 to pi over 3 of the square root of 1 plus negative tangent of x squared square rooted dx. And then notice that this is 1 plus tangent squared of x square rooted dx 0 to pi over 3. There's your length. By evaluating this integral, we find the length. And this shouldn't be too bad because you can see that we're going to be able to use some Pythagorean identity here to simplify this. And there you go. So in the next video, we'll actually do some of these examples. We're going to find lengths of curves. And we're also going to define something called the arc length function.